Imagine a line of students, each with a sandwich preference, facing a stack of sandwiches. Can we figure out how many students will ultimately miss lunch because their preferred sandwich isn't available? We're given two arrays, one for student preferences where 0 means circular and 1 means square, and another for the stack of sandwiches, also 0s and 1s. Students take turns at the front of the line. If a student likes the top sandwich, they take it and leave. If not, they go to the back of the line. This continues until no student at the front likes the current top sandwich. Our goal is to return the number of students who couldn't eat. A straightforward approach uses a queue for students and an index for sandwiches. We repeatedly dequeue a student. If their preference matches the current sandwich, they eat, and we advance the sandwich index. If not, they're re-queued. We need a way to stop, so we track consecutive failures. If the number of consecutive failures equals the remaining students, no one can eat. This approach, while functional, might re-queue students many times, leading to a worst-case time complexity of O(n) squared, because each student could cycle through the queue multiple times. Space complexity is big O of n for the queue. The key insight here is that the asterisk order asterisk of students only matters for who is currently asterisk at the front. What truly determines if students can eat is simply the asterisk count of each preference type versus the asterisk count of each sandwich type. We can pre-calculate how many students prefer circular sandwiches and how many prefer square ones. Let's use an array of size 2 for this, where index 0 stores the count of students wanting circular and index 1 for square. We iterate through the students once to populate these counts. Then, we iterate through the sandwiches. For each sandwich, if there's a student who wants it, we decrement their preference count. If, however, we encounter a sandwich type for which there are no remaining students with that preference, then all subsequent students with different preferences also cannot eat. At this point, we can stop and sum the remaining counts in our preference array. Let's trace this with students, 1, 1, 0, 0 and sandwiches, 0, 1, 0, 1. First, we count student preferences. 2 students want circular sandwiches and 2 want square. Our count array is now circular count 2, square count 2. Now we process sandwiches. The first sandwich is 0, a circular one. We have 2 students wanting circular, so 1 eats. Circular count becomes 1. Next sandwich is 1, a square one. We have 2 students wanting square, so 1 eats. Square count becomes 1. Third sandwich is 0. 1 circular student remains, so they eat. Circular count becomes 0. Final sandwich is 1. 1 square student remains, so they eat. Square count becomes 0. Both counts are now 0. Since both circular and square counts are 0, no students are left who couldn't eat. The total number of students unable to eat is 0. This is correct as all students found their preferred sandwich. You'll often spot this counting pattern when the asterisk-specific order asterisk of elements becomes less critical than the asterisk overall distribution or frequency asterisk of element types. If the problem involves matching types and the order can effectively be shuffled without altering the final outcome, consider a counting approach. This optimized solution runs in big O of n time because we iterate through students and sandwiches once. It uses big O of 1, constant time space, as our count array is fixed size. This counting trick simplifies what initially seems like a simulation problem. Try the next problem to reinforce this pattern, and don't forget to subscribe for more concise DSA explainers.